Okay, again, applications of stoichiometry. This time, this is the more practically focused topic. We'd be doing a titration if we were in class. Now, understanding these questions means you need to understand the glass web. So, let's have a go at seeing what the different types of glassware are, what they're used for. Volumetric flasks. Large volume, designed to measure large volumes exactly. So since I'm here at school, I'm right as well. In the classroom, I'd point to the display up on the side. That's a volumetric flask. This is a 500ml volumetric flask. So you'll add a small amount of something and you'll make it up to the graduation line with distilled water and then mix it to get an exact dilution done. Pipette. Pipette is again used to measure fixed volumes, exact volumes, commonly a 20ml pipette. We use a pipette filler to draw the solution up. It's got a bulb. You draw up the solution till you hit the brown graduation line there, and that will give you, in this case, exactly 20 mils. So we measure the volume exactly, and it's a fixed volume. That pipette will only measure 20 mils. Now, when you're given a question in this topic, it's understanding the words which is critical. So the volume that a pipette dispenses, so that 20 mils that will come out of that pipette is called an aliquot. And knowing that if it's an aliquot, it's come out of a pipette, is critical to figuring out what's going on in titration questions in volumetric analysis. Burettes have got a scale on them. You start at one point on the scale, you finish at another point on the scale, and the volume delivered is the difference between them. So again, I've got the one from the display on the side here. It's got a tap down the bottom. You let the solution run out for a certain point. You turn off the tap when the reaction reaches the end point, and you measure the initial volume, you measure the final volume, and the volume added is the difference between them. So again, it will measure exactly again, hopefully to 2 decimal places, 4 significant figures there. Now, the volume dispensed by a burette is called a titer, or a titer if you like. Again, another word that you need to understand. Titer, the volume delivered by burette. More terminology. If it's a standard solution, it's a solution that we know the exact concentration of to at least 3, usually 4 significant figures. Okay, so let's go through it. Now, this is the standard setup for a titration. So if you've got HCl solution that you don't know the concentration of, you're going to put that HCl into the burette. The standard solution that you do know the exact concentration of, we know the concentration of this sodium carbonate is exactly 0.100 molar. Now we're going to measure 20 mils using the pipette and put it into the conical flask. We're going to add a few drops of an acid-base indicator. Then we're going to very carefully add our HCl. And when we've added just enough HCl to exactly neutralise the sodium carbonate, the indicator will change colour. We'll stop adding at that stage and we'll record the volume. So at that exact point of neutralisation. Now, this is the standard setup, which is why I'm asking you to copy out this diagram into your book. And in that question, you'll get this magic word aliquot. The aliquot is what's added to the conical flask. That is how you work out which chemicals what has happened. The titer is going to be the volume that comes out of the burette. So if we've got an aliquot of sodium carbonate, that means we know that that's gone in the conical flask and that the other stuff has come out of the burette. Now we could have done this with the sodium carbonate going into the burette, with the acid going into the conical flask. That's a practical consideration. We're doing it this way around now. But the diagram's always going to look basically the same. You're going to have a solution, you're taking an aliquot using a pipette into a conical flask, the other solution goes into the burette. And a very quick sketch diagram like this helps you to organise the information, especially as the problems get a little bit more complicated, as they will in Year 12. Now there's a process of working out a standard sodium carbonate solution. If it was in class, I'd actually get you to do this now, chuck your lab coats on, etc., and make your standard sodium carbonate solution. And at that point, we've got a meniscus. So we fill up the volumetric flask till the level of the liquid reaches that graduation point. Because of course there's a curved surface, a meniscus, on any body of water in a tube, but it's the bottom of the meniscus, bottom of that curved surface, which needs to be on the line. Just one of those practical considerations. Using a burette, this is one thing I always emphasise, reading a burette to 2 decimal places. I'd be harassing you during the prac, telling you to read it to that 2nd decimal place. And some of you would find that easier than others. Two-handed burette technique again. These are practical considerations. Going slow around the end point. You've got to get consistent results in this, so being very careful near where the colour's going to change is critical. The titer, the volume that you're going to use in your calculation is the difference between the initial and the final volumes, and the emphasis on doing things carefully. If you want to get valid results, you need to have concordant titers. That means the volume added each time, you need to do it 3 times and get the volume added within 0.1 of a mil, which essentially means 2 drops. Now that's a challenge. Hopefully we'll get a chance to do that in class. Now the acid-base indicator that we use is simply a chemical which changes colour. When it changes colour, we end the titration, and we choose one that's going to change colour really close to that exact point of neutralisation, the equivalence point. Okay, so the calculations that we get run something like this. HCl solution was standardised. That means that's what we were trying to work out. What's the concentration of our HCl? Standardised means produce a standard solution, which means find its exact concentration. By titrating 20 ml aliquots of standard sodium carbonate solution. Magic word, aliquots. So what went in the pipette? Sodium carbonate. That means the HCl went in the burette. The titer is what came out of the burette, so that means 17.83 mils is our volume of HCl. And we can put it all together to work out the concentration of the HCl. Now, a lot of information there. And again, I really encourage you to do a very quick, rough sketch diagram. Doesn't need to be exact, doesn't need to be precise, doesn't need to be neat and tidy, I should say. It needs to obviously have the right numbers on it, in the right places, but just to schematically organise your information. Now, what are we being asked for? Concentration of the HCl, as I said. And draw a diagram. I really think that visual representation of this information is critical. Now, if you can do it easily, if you get the right answers every time, I don't care how you do it, but until you get the right answer every time, I think a diagram is the best way to do it. And, you know, did this on a drawing program. Doesn't have to be that neat. Again, if we were in class, I'd be showing you how rough it could be, but still has the sodium carbonate, the aliquot sodium carbonate over this side. So 20 mils, concentration 0.1 molar, that's all you need. Very rough volumetric flask, very rough pipette going into a very rough conical flask. Then the HCl going into the burette, doesn't need to have anything fancy, you don't need to draw the tap even. Just put in the volume, tell us that it's HCl and that it goes into something vaguely like that. Diagrams are really important. An equation, mole ratios, like I say, most questions you'll be given this, so don't stress too much about that. And once you've got all the information organised, once you know what's what, then the calculations are pretty easy. Calculate the moles of the standard solution. So that's the only moles you can work out from what you're given. Now you're given the volume and the concentration of your sodium carbonate, that's where you can work out the moles of. So that's the first step of any stoichiometry problem. Moles from the given information. In a titration, it's always moles of the standard solution. Second step, want over got. In this case, we're after the HCl, so want over got 2 over 1 to give us the moles of the HCl. Once we've got that, we work out the concentration of the HCl. So the volume of HCl, C, the value of a diagram means you can go straight to that diagram. How much HCl did we need? What volume did we have? Well, it's on that diagram. 17.83 mils turned into litres. And that gives us our concentration. Now, it's really important that you have a go at these questions. I am going to run through them, so I would pause the video now and go through and do it, then come back and check your answer. That's the question, and that's the second question. So I'm asking you to draw diagrams. The first diagram will look like that. So again, 20 mil aliquots of the base. What is the base in this reaction? You're given the equation there, so the base is clearly the sodium hydroxide. We're titrating with sulfuric acid. That means titrating with means the sulfuric acid goes in the burette. But the key thing to organise the information is the fact that it's aliquots of the base. Aliquot is the pipette, and that the base is sodium hydroxide. Okay, so that's the diagram, organising information nicely. If that's enough of a hint for you now to go and have a go at the question, hopefully you're going to get that answer. Okay, I might just run through that if it doesn't appear on the slides. So, let's see, we can do it here. Moles of the standard solution. Of H2SO4, of course, which equals 0.153 times 0.02466. That equals, to get the calculator out here, 0.153 times 0.02466 equals 3.77 times 10 to the minus 3 moles. What have we got to get moles of the sodium hydroxide? So it's going to be want is sodium hydroxide, which is 2, over got, which is a sulfuric acid, which is 1. So I shall multiply my previous answer by 2. 7.55, that'll probably round to. Then to work out the concentration of the sodium hydroxide is the moles divided by the volume. So that's simply dividing my previous answer by 0.02. And funnily enough, 0.377 molar. On to the second question. That's our diagram. The standard solution of sodium oxalate is used to titrate 20 ml aliquots of a nitric acid solution. So the aliquots are of nitric acid. That means nitric acid is over this side going into the conical flask. The standard solution is the sodium oxalate, which therefore must be going into the burette. Standard solution is the one we know the concentration of. We're given the concentration, and the titer has to be that volume coming out of the burette. So again, those magic words. aliquots of a nitric acid solution. That means the nitric acid was over this side going into the conical flask. Then we can go ahead and do our calculations. Hopefully that'll be enough of a hint for you to go ahead and do the calculations. Like I say, getting that diagram just makes it so much simpler. So we start off moles of our standard solution. Equals concentration times volume. Onto the volume, I automatically put it into litres because I know I'm going to have to do that, and if I put it there straight away, I know I'm not going to forget doing it later on. .095 times 0.01671 equals 1.59 times 10 to the minus 3. Concentrations, 3 significant figures there, so I'll be writing my answers to 3 significant figures. So what have I got to get moles of the unknown, the nitric acid? Again, it's 2 to 1 mole ratio from the equation. And you'll note I'm not rounding off during the calculation. Just taking that previous answer, it's already on the screen on my calculator, and I'm multiplying it by 2 to get that. And then the third step, of course, is calculate the concentration of our nitric acid, which is the moles divided by the volume, already nicely in litres there for us. So divide that previous answer by 0.02. And, oof, I ran it off incorrectly there, didn't I? Happens to the best of us. And that's volumetric analysis. That's the basics of volumetric analysis anyway. The more complicated versions involve doing dilutions, and that's because the solution that we want to standardise often is too strong, so you've got to make a dilution. So you get a nice, simple titration. Now, it's these sort of questions where diagrams become even more important. If you want to figure out what's going on, it really does help if you've got a diagram. So what happened? 20 mils of an unknown nitric acid solution is diluted to 250 mils. And then 25 ml aliquots of the diluted nitric acid solution are titrated with sodium carbonate. So what are the aliquots that we titrated? Nitric acid. Nitric acid goes into the conical flask. Sodium carbonate goes into the burette with that volume. Now, we've also got to put in that dilution information. So we've got an unknown nitric acid solution. We took 20 mils diluted that to 250, and then took 25 mils of that diluted solution to go into the conical flask. So getting the chemicals around the right way from the start, aliquots of nitric acid, that's your key bit of information. Get that diagram. Don't have to be as fancy, don't have to shade your burette or shade your conical flask. All it has to be is really quick, simple, schematic. So we had our unknown nitric acid solution. We took 20 mils, diluted it to 250 mils, then titrated 25 milliliquots of it. Now, going through the calculations, it's not that much more difficult when you've actually got all that there. So we start off with moles of our standard solution. It's easy. Want over got to get moles of our unknown. So that's moles of our unknown in that conical flask, in that 25 ml aliquot. So we can work out the concentration of that 25 ml aliquot fairly simply. That's the volume that reacted, so that's the volume that we use. That means the concentration of the aliquot is that 0.2127. And where did that solution come from? Well, that's the same solution that's in our volumetric flask here. So we know the concentration of that volumetric flask is 0.2127 molar. We need to work out the concentration of the original solution. How do we do that? Well, it's a simple dilution. 20 mils has been diluted to 250 mils. That's a dilution factor there. So we work out our dilution factor and then multiply to get the original concentration. Original concentration, of course, is higher, so we're going to multiply by our dilution factor. So just think, where did the dilution occur? The dilution occurred when we add the 20 mils to the 250 mils and then filled it up with water. So that was the dilution step. So that's our dilution factor, 250 over 20. And like I say, like I keep on saying, diagram organises that information, makes it so much easier. Okay, question. Now, take that scenario, hopefully be able to do it all for yourself and get that correct answer. So pause the video now, and if you can, let's just do it. If not, I'll go through it. So I'm going to, of course, start off with the diagram. So what have we got? 10 ml aliquot of sodium hydroxide is diluted to 250 mils, and then 20 ml aliquots are titrated. So that means we've got the sodium hydroxide on the conical flask side of it. This is how quick and simple my diagrams are. So we did a dilution of our sodium hydroxide, so that's our volumetric flask. What's the size of our volumetric flask? 250 mils. Then we took aliquots. We titrated aliquots. What are the size of our aliquots? 20 mils. we prepare that dilution? We had an initial sodium hydroxide solution, and it was, we don't know the concentration, question mark molar, and what did we do? We took 10 ml aliquots, diluted it to 250 mils. And what do? We titrate it with the sulfuric acid. So the sulfuric acid, of course, has to be in over this side. This sodium hydroxide is on the other side. Concentration we're given 0.7788. The volume is the average titer, 14.64. Let's whip that straight into litres so we don't forget later on. And that's our information. Once we got to that stage, hopefully have a go at working it out from there. Pause the video. And if not, I'll go through the working out steps. First step is always moles of the standard solution. Moles of, I'll actually say what I'm calculating here, moles of sulfuric acid equals times the volume equals 1 point. Now we're 4 significant figures right throughout this question. So the lowest number of significant figures in all of the data that we'll end up using is going to be 4. So I'll be expressing everything to 4 significant figures. But of course I won't be rounding off. I'll be continuing to use those answers on my calculator. So second step is to work out the number of moles of diluted sodium hydroxide in the 20 ml aliquot. What have we got? It's 2 over 1. Next step is to work out, we know how many moles of sodium hydroxide were here. We'll work out the concentration of the dilute. Do I have a better whiteboard marker? I do. So is the moles divided by the concentration? Sorry, what am I saying? The moles divided by the volume. So it's the volume that we actually titrated. And gives us that. I'm going to run out of space here. I can move over. Okay, so that's the concentration of our diluted sodium hydroxide. What was the concentration of our original sodium hydroxide? Well, the dilution that we did was 10 mils was diluted to 50 mils. So our dilution factor equals 250 over 10, which is 25. So our original, the concentration of sodium hydroxide equals 25 times 0.1140, which is 2.850 as it says there. Like I say, there's a bit to these calculations, but if you've got a diagram, you're halfway there. Something a little bit neater. And that's volumetric analysis.